All right, so let's talk about a word we use all the time, eventually. What does it actually mean when it's buried deep inside the software that runs, well, everything? Today, we're going to look at how computer scientists are taking that kind of vague promise and turning it into a concrete, provable deadline. Let's get into it. Right, so this is the huge puzzle at the heart of building systems you can actually rely on. If a program promises your data will eventually save, or a server will eventually get back to you, how can you be sure? I mean, if eventually has no time limit, if it could mean forever, is it even a real promise? Not really. And look, this isn't just some abstract thought experiment. This is a massive challenge in what's called formal verification, which is basically the science of proving that software does exactly what you think it does. Just think about it for a sec. You wouldn't want your self-driving car to eventually apply the brakes, right? Or for your bank to eventually process a transaction. That could be a total disaster. In the biz, these are called liveness properties, things that absolutely must happen. And for those, a mushy, vague, eventually is a huge liability. We need a way to prove they'll happen on time. So how did we even start to solve this? Well, computer scientists came up with some pretty powerful tools. The classic method involves mapping out every single possible future, which you can think of as trying to explore this massive, sprawling, literally infinite forest. Okay, so the main tool in the toolbox here is something called Computation Tree Logic, or just CTL. It's a really precise language that lets us talk about all the different futures a system could have. It's like having both a map and a special language to describe every single path and branching trail in that infinite forest. And this forest analogy, it perfectly nails the problem. Using regular CTL, you can actually prove that no matter which path you wander down, you are guaranteed to eventually find a sunny clearing. That sounds amazing, right? A solid guarantee. But, and it's a big but, it doesn't tell you if that clearing is 10 steps away, or a million, or some number so big you can't even write it down. There's just no deadline. So what's the fix? How do we solve this? What if we just change the rules of the game? What if, for our trip through the forest, we add a hard deadline? It all boils down to this one simple but honestly game-changing idea. We're not just saying, oh, you'll get there. We're saying you will get there, and I personally guarantee it will take no more than K steps. All of a sudden, that promise has some real teeth. And of course, this cool new rule has a proper name: Finitely Bounded Semantics for CTL, or just CTL-FB for short. It totally redefines that word eventually. It's not an infinite, fuzzy promise anymore. It's a finite, measurable, solid commitment. Okay, so what does this actually look like in practice? It's basically a three-step dance. 1, the system makes a promise that something will happen. 2, we set a hard deadline, a number we call K. And 3, the most important part, we check it. We verify that the system actually meets that promise within K steps, no matter what happens. See? It's way, way more rigorous. Now, you know there's no such thing as a free lunch, especially in computer science, right? Making a change this fundamental to a logic has to have some consequences. So let's check out the trade-offs. And that's a totally fair question to ask. By making our promises stronger, are we accidentally making the logic weaker or making the problems even harder to solve? Okay, so take a look at this comparison. The really interesting part is that first line. By adding this finite deadline, CTL-FB loses a really important theoretical feature called the finite model property. Now, in simple terms, that's a mathematical guarantee that helps with certain proofs. That sounds bad, right? Like we broke something. But here's the twist. Most of the real-world systems we actually want to check, a chip in your computer, a network protocol, they are already finite systems. And when you're dealing with those, it turns out the two logics are basically equivalent. So in the real world, for the stuff we actually build, that theoretical problem kind of vanishes. All right, but what about how hard it is to solve? I mean, we added a rule, a constraint. That's got to make things harder, right? Well, get this. Both of these logics are what's called XPTIM complete. That's a fancy way of saying they both belong to the exact same class of computational difficulty. They're both really, really hard problems, but one isn't fundamentally harder than the other. And that right there is the big surprise. We get a much stronger, much more useful promise, one with a real deadline. And we get it without making the problem fundamentally any more complex to figure out. In the world of practical verification, that is a huge, huge win.
So this is way more than just a cool idea from a logic textbook. This whole concept of adding boundaries and deadlines has a massive impact on how we actually go out and find bugs in real systems.
And that brings us to something called bounded model checking, or BMC for short. It is an incredibly popular technique used all over the industry. Instead of trying to explore that whole infinite forest, BMC says, you know what, I'm just going to check every single path up to, say, 100 steps long. It's the real-world application of our whole deadline philosophy, and it's used to hunt for bugs within a scope that actually makes sense. And it turns out, this whole idea of adding bounds, it's not a one-off. It's part of a much bigger trend in the field. You've got logics like prompt LTL, which, you guessed it, demands things happen promptly, or mission time LTL for things like spacecraft with hard mission deadlines. They all share the same core idea. Let's make our promises about time concrete and actually measurable. And really, that's what this all boils down to. Whether it's through a formal logic like CTL-FB or a practical technique like bounded model checking, the end goal is exactly the same. It's about getting away from these hopeful, vague promises and moving toward hard, provable guarantees. This is how we build technology that we can actually trust with our lives. So let me just leave you with this final question. For the operating system in your phone, the control systems at a power plant, the software running life support in a hospital, what would you rather have? A vague hope that things will work out eventually, or a verified mathematical proof that they will work within a specific, guaranteed deadline? Yeah, I think the answer is pretty obvious. Thanks for tuning in.